Okay.
So I can't even.
So we have 43 responses. Donald? I'll let you in.
It's not because of that, but it's just
The app is stalled.
Yeah, I've reset it a couple times. This is all I get.
Okay. If it's not opening in a browser, try a different browser, maybe. And then let me know throughout the class it doesn't change. So I want to see the responses. So we have, it looks like a lot of people were kind of in the middle on a 1 to 5 scale. One of the most important skills, I'd say, in life in general is to know what you're capable of. And so to do that is, if you feel like you were in the middle, like a 3 or a 2 or a 1, which we have some 1s down here on the scale, I would really like for you to think about what it is that you did coming into the exam, why it is that you felt a certain way. Either you felt that you were not confident and you did really well, or the other way around. We don't want that to happen. Stuff happens in life, right? There are certain times where you come in and you say, you know what, I just wasn't able to prepare as much as I thought. I know that I'm not going to do as well as I'd like, but I know what I'm going to be able to do. That is one thing, right? That's why we have the exam replacement policy, because sometimes you don't do as well as you are potentiated to do. But if you think you're going to do really well, you think you're going to knock it out of the park, and you go home and you get a score and it says otherwise, then that's a really big mismatch. So what I want us to think about is, for those who didn't necessarily do as well as they wanted, for either of those two reasons, thinking about this entire class, does less than ideal score on exam 1 mean that you're really not going to be able to pass this class? What do you think? Talk to your neighbor for a second. Get the jitters out. So what are our thoughts on this kind of question? Does less than ideal performance on this exam mean you're done? You should drop out, you should withdraw right now.
No.
It's not an option.
You can withdraw, I think. You just don't get any of your money back. So the big answer is no. It doesn't at all mean that you're going to fail. Why? What are some things that are in your favor? Okay, so let's talk about a couple different things. The resources that will help you practice to get up to speed. Okay, that's one way to look at it. So you have homework, and there are the dynamic study modules that are additional practice problems. There are tutoring, there's Math Assistance Center, there's office hours, and if I don't have enough office hours, they don't work, I need to hear from you to tell me when to have those. I added 1 extra office hours last week, but maybe I do an online office hours where I'm just there, you can drop in with questions, and it'll be a link you just click on. I'd be happy to do that if people work, and it would have to be at night, we can do that. What about the things that, grade-wise, can still mean that you can succeed in this class? So the mastering homework is worth 16% of your grade. 2/3 of that is for completion. So if you're looking at your overall weighted grade in the class right now, there's that one category that says weighted grade. That's based off of the different weighting of the categories, right? That mastering is for 16% of your grade. So if you're in Blackboard and you look at your grade, look at the weighted grade, that'll give you a real idea of where you stand. Tonight I'll try, or tomorrow I'll update your clickers, your mastering homework, and your exam. So now you have something in all the categories. At some point in the next week or two, I'll ask the TAs to provide your lab scores as well, so you really can get an overall picture of where you stand in the class. So 16% of your grade, 2/3 of that comes from just completing the pre-class quizzes and the homework. So that's a lot that can help you with your grade. The post-class quizzes, those are based on what you can do, so that isn't just for completion. But if you keep up on the other stuff, there's a good chance you'll do better in the post-class quizzes. What else will help you out grade-wise? Clickers are 7% of your grade. You just got to be here and participate. If you don't participate, you're not going to get credit, but you got to be here and participate. What else?
Isn't it morning exam, like your final cancel out the exam? Or?
Yeah, so your lowest exam score, if it's worse than your final exam. So, for instance, if you got a 50% on this exam, and you show me by the end of the semester that you can do better than that, and you get a 65 or a 70 on the final, or even higher, then that final exam score becomes also your exam 1 score. It duplicates. So in essence, it drops your exam 1 score. Or if you did really well this time, but something really big gets in the way for the next exam, and you just don't do as well as you want, then it'll replace your exam 2 score. Right? So it's a way to kind of give you some breathing room. But right now, if you did not do as well as you wanted on this exam, it is a bit of a wake-up call to say whatever you've been doing, you might need to add to that. You might need to figure out other ways to study more effectively, not necessarily more time, but more effectively in order to do better on future exams. Monica, you have a question?
Okay, I do have a question. A while ago you said that, did you say the pre-tests are based on completion?
Yeah.
So does that mean?
I mean, you have to get it right, but if you get it right after 3 tries, you get full credit for that. So, unlike the post-quiz, you only get 1 try, and then you don't see the answer until the midnight on Monday, and then based off of that, you get whatever score you got the first try around, right? So, I want us to have a small set of discussions. What do you think we can do for this? What do you think the students, I guess anyone, can do to improve your chances of having a better outcome in this class? So talk to your neighbors, have some small conversations. What are the things that people might be able to modify or add or do differently in order to have a better chance of success in this class? Just wait until you see the score and talk about it.
Every breathing moment. We're dropping out of every other class. We're dropping out of every other class. We're doing nothing but killing. Not as well as I would have liked to. I got a 90 something on that. 60.
Just on the final. All right. I'd love to hear some of the conversations that you had. Tay.
We knew which topics we weren't good at, but we were like, we'll just handle it instead of going into tutoring, which is the resource we have. So.
Yeah, so where do you find the tutoring hours for chemistry?
It's on the first page of Blackboard.
Great. Our Blackboard homepage has hours listed there. If you don't think the first person you go to is the best fit with you as far as their capabilities of tutoring, try another one. Don't say, oh, chemistry tutoring is not going to work. There are different tutors. They have different levels of training. They have different styles of interacting. So try out a couple before you give that up. What else? What are some other ways we can address some of those things we might have seen? Ooh, I don't think I'm very confident in that. I should do something about it. Carmen?
With me personally, I don't know about anybody else, but I should actually read the chapters.
When? This is very important. No, so it's a really important point. Most people pay a lot of money and complain about how expensive the book is, and then we don't read it. So when is a good time to read the book?
Before I come to class, like before I actually, I would say like that week of class, like or either that weekend. Since you're coming on.
So how do you know what to read, though?
You have it in there. You have it on there. You have it on the Excel sheet.
Okay, so there's 2 different ways you know what to read before coming to class. One is in Blackboard on the far left side, there's a reading guide. Click on that and I should have it updated. I got pneumonia last week, so I didn't update it until today, last night. I'm standing upright, I'm good, right? Antibiotics, chemistry at work. This is what I look like with pneumonia. No, just kidding. If you'd had to see me teach last Wednesday when we had the exam, it would have been bad. So that reading guide should be populated at least a week in advance. The other place, the pre-class quiz. That primer The reason I give that to you is that's going to be what we're talking about in class. So if you look at that and this gibberish to you, you should probably go read. And how do you figure out what to read?
Review.
There's that review button in that top right corner. Click that. It'll bring you right to the book. If you don't have the digital ebook, but you decided to buy a physical book, it'll tell you what chapter 3.8, 4.2, whatever it is. And it'll give you the name or the title of it. You can either Google a YouTube video, Khan Academy, you can use another book. I don't care where you go to get your info. If you don't have any chemistry book, I think you're going to be in a disadvantage in this class. If finances are an absolute hurdle for that, come see me. I can lend you a book. If you could spend 20 or 30 bucks on a book, I can make some suggestions. Either the book we have, like an older version on online somewhere, you can find it for 20 or 30 bucks delivered.
I think I rented the new one for that price.
Yeah, if you rented it through the bookstore, it's like 150 bucks. But if you rented it elsewhere, it was like 30 or 40 bucks. So there's a lot of different ways. Okay? And so that idea of coming into class with at least a little bit of knowledge of where the words are going to be and like what they might be related to is going to be a huge leg up. Because in class when we talk about it, it's not just going to be like trying to keep up, right? I don't want you to read and understand everything before you come to class. If you did, you wouldn't need me. I don't think you really do need me, but I'm here to help make things easier. So read a bit before class, skim through it at least, if that's all. If you only have 10 minutes, skim through those chapters. That's it. And then after class, being like, I'm still not really sure on this. Going back to the very first question, right? The more quickly you can identify what you don't know how to do, the easier it's going to be to address those things and make those your strengths instead of your weaknesses. And then after class, you can go and you can read about some of the stuff that might have not been so clear in class, or look up some practice problems. Other ideas for how to make sure that we crush it next time around?
Learn how to use the calculator.
Legit, learn how to use a calculator. And I would say along those lines too, even if you knew how to use it, I saw a lot of people with scientific notation just writing stuff down and they didn't know what they were doing. So there was a few examples where I saw in the short answer where people had a number, but they didn't know what to do with it. And so even though some of the process was right, I didn't give any credit because you have to show me you understand what you're doing. So there is a dynamic study module on sig figs, which is just a barrage of questions to help get you on top of it. There's a ton of questions on scientific notation. If you don't feel comfortable with those, don't lose credit throughout the entire semester on that, please. Dylan, you had another comment?
You get sleep.
Get sleep, especially before the exam. Agreed. Lena?
I think, like, my problem is, like, I'll say, I need to study after I finish this other thing, and then it turns into another thing, and it turns into another thing. I need to set aside, like, specific times during specific days in order to study.
Even if you can only set aside, like, say you did something crazy, like 15 minutes a day, 7 days a week, you'd end up a lot further ahead than you think from having such short time windows. Sometimes it is good to sit down and really dig in, but sometimes even just a little bit of interaction. It's actually, there's a technical term for it called interleaving, where you do a little bit of something and then something else. And by coming back to it more frequently, it actually helps solidify it in your memory. It takes it from short-term to long-term memory, which is where you need it in order to use it, to operationalize it. Anyone else have? Jay?
I think for me, like, at first I felt really, really confident about this exam. And then I started getting with other people in class, and they were saying stuff, and I was like, oh, really? I don't know that. So when we went over, like, examples of, like, them explaining it to me the way that they understood it, it helped me understand stuff.
So are you saying that studying in groups is helpful?
Yes, for sure.
Great. So some of that we do in class, but if you were able to find people with a similar schedule to you, then that would be extremely valuable to find time once a week. Sit down for an hour in the library after class, before class, some other class you have overlapping, and just work through some of the problems. If you have a question, ask it. It's amazing what that conversation will bring out that you didn't know that you didn't know. If you don't know it, you can't address it. All right. Any other thoughts or comments on this?
I have a question. How do you figure out if you were trying to figure out on your own what you made on that test?
Don't worry about it. I'm going to post it right after class.
Okay. I mean, I was just saying, you don't add the points that you got on the shorthand to
So for multiple choice, I gave you a percentage. For the short answer, you would have a total number of points. You'd have to do a weighted average of the two, if you will. So you can figure out how to do that, because I think you know how to do weighted averages. Bradley?
Taking notes during class. That's what always helps me.
Okay, and I would argue that you're kind of forced to take notes during class, because you have the worksheets that you actually go through. But make sure if there's something, especially going back to this idea at the top here, if there's something in class that you're like, what the heck was that? If you think it's too disruptive to ask a question about it, write down the topic, put a star next to it, and come back to it on your own time. Or send me an email, or post a discussion board after class. You mentioned something about steric number in class, and I'm just totally lost. Like, can you fill me in on that, or can you give some resources? And I'll post stuff on the discussion board. That would be a great way to do so. Okay, so take home of exam 1 is 1, put it away. Okay. So I don't want you to be distracted. We've already spent almost 20 minutes of class talking about it. I don't want us to focus on it during class anymore. Number 2, I want us to be realistic and say, if you did not do well in exam 1 or as well as you wanted, it's not the end of the class, end of the world by any means. But it also means it's a wake-up call, and you got to figure out what to do if you really want to crush it. I would love to have everyone in this class get a B or higher. That would be a dream to me. And I feel like my job is to try to get as many of you as close to that as possible. Okay? My job is not to penalize you if you didn't have a great background coming in. So let's try to figure out how to make that happen. Historically, this class has not been the highest success rates, and I hope that we can prove that we can do better than what's been done historically. All right, so our class today is going to be building off of some things that you've done in lab this last week. Did anyone feel like your head was underwater in lab this last week?
Yeah.
Okay, well, hopefully it'll be a good starting point for today. We did a little bit with Lewis structures and the beginnings of it last week. You did a decent amount in lab, and now we're going to get you to the point by the end of this week where you should be pretty confident drawing a Lewis structure and telling us some stuff about what it means now that we can draw it in 2 dimensions. What does it look like in 3 dimensions? So that means that I need you to be able to draw a Lewis structure. And here's the caveat that's going to... Do I like you to memorize everything? Is that important to me? I need you to know how to do processes. But there's 2 sets of things that I want you to memorize. 1, metric system. It was a bit rough on the exam, but I think I haven't had my classes do that in the past because they weren't specifically nursing major oriented individuals. But you need to know that. Like, you really need to know that. So that's why you in this class have to memorize it. The second thing is polyatomic ions. They're these little molecules that are made up of a few atoms. Poly means more than one, right? So polyatom, polyatomic ions. So all of these subclass of molecules, so we're talking about small molecules and small molecules that have a charge on them. There's going to be a short list of those that you're going to need to know what they mean. It's part of the language of chemistry. So I want you to know, when I say phosphate, I want you to know what that means, and I want you to be able to draw that molecule. Can you have those on your note card for exam 2? No. Or exam 3, or exam 4. So polyatomic ions is another small category, and this is one you might want to make flashcards for what the formula is. Once you have the formula, you should be able to draw it very easily after we go through the next couple days of class. And then along those lines too, Lewis structures are all 2 dimensions, right? It's drawing something that is flat. It sits on a piece of paper or a plane. But that's not how molecules exist in the real world. Molecules tumble, they roll around, and so we want to be thinking about what do they actually look like. If we were to take the magic school bus and zoom in and see these little molecules, what are they going to look like? How do they interact? And it's based off of the fact that they don't look like this. They're not a sheet of paper that has 4 hydrogens sticking out like this from a central carbon. So to do that, we're going to need to be talking about the steric number in the AXC group that we mentioned at the end of last class, and you've worked with some in your lab. So this was on the end of last week's worksheet. we're going to do a couple questions off of that. I think I also printed it onto today's worksheet. So you can go ahead and try drawing this molecule and then answer the question what the steric number is around carbon. We have 5 people here to help today, and your peers. So if you get stuck, ask the people around us. Ooh, we have 6 people. And remember to try to use the approach where you determine how many bonds based off of the S equals N minus H. Does anyone not have their exam back yet? Anyone missing their exam? Does anyone want to build a glucose molecule? You have 9 responses. Make sure, one, you can draw the Lewis structure if you know what N and H are. And then figure out how many bonds.
They're only doing, they've done all but their quizzes. They did a quiz.
We're on question number 3 in the worksheet. So basically everything except those. Ask Mel. Let's make sure we're on the same page moving forward so that no one's spinning their wheels. Looks like we have 41 responses. Does that mean that everyone got to a point? Okay, so let's talk through the Lewis structure first before we get to this. So what is the number N? What did you get for this one? What's that, Lena? 40. So you said N equals 40 electrons. Why?
Because you have to add the octet rule. So it's 8 plus 16 plus 16.
So it's assuming the octet rule or duet rule if it's hydrogen, remember? So we know that the carbon, if it's fully stable, has 8 electrons around it. Hydrogen, each of the 2 hydrogens has how many electrons? 2. So that's 4 more electrons. Each of the chlorines would have how many total electrons around them? To be totally stable, they would have to have 8 around each one. That's the N. So that's 24, 28. And then our H is how many we actually have that come from the valence electrons from each one. So how many would that be? What's that?
20.
How did you get 20, Rakai?
So the carbon has 4 valence electrons, the 2 hydrogen have 2 total, and then the 2 chlorine have 7. So 14.
Great. So that's 4 plus 1 is 5, 6 plus 14 is 20 electrons. So we're basically trying to draw this molecule with 20 total electrons, but somehow it has to kind of look like we have 28. So how many of those 20 have to be counted twice? So if we find the difference between those, I don't know why I put a line there, then we know that the shared electrons is 8 electrons. That means that out of those 20, 8 of the 20 are counted twice because they count for one atom and for the other atom. So how many bonds is that? Okay. Could we have predicted that for this molecule? This molecule might have been a bit easier. We didn't necessarily need to do this because when we have a carbon and 4 things, it's usually like I drew over there with that methane molecule, carbon in the middle, 4 things around it. Lena?
So the steric number is the number of bonds, or is it the number of shared electrons?
So steric number is the number of electron groups around an atom. So we'll get to that in a little more detail once we draw this out. So now that we know we have 4 bonds, can I go ahead and erase the math here? I'm going to erase the math. We're going to draw carbon in the middle. Why? Because carbon is almost always in the middle. And the least electronegative atom is in the middle. We talked about electronegativity last class a little bit, so that's something that we'll spend a bit more time with. Let's draw 4 bonds. What do we put at the 4 bonds? Does that look good?
Wouldn't they be on opposite each other?
So then I hear maybe they should be like that. Which one of those two is right? Why both? All right. We talked about 3D in this lab this last week, right? If you build these 2 molecules, it turns out they're identical. Because 2 of these are coming out towards us, 2 are going back. And so if you looked at both of these molecules and you kind of moved them around in space, they're actually the exact same thing. They're identical. There's times, if you go on to take organic chemistry, which I don't think most of you are, well, you'll find that depends on if each one of these is different, then that's not necessarily true, because then the order that they show up in space, you can't get them to actually look identical. So, that's fine? That's fine. Are we done?
No.
What else do I need to do? Okay, so we had a total of 16 electrons, right? Out of those, we know that shared... Oh, wait, sorry, it's 20 electrons, right? We had 20 total electrons. Shared electrons were 8 of those. So how many are not counted for yet? So we had 20. 8 of them are now drawn out.
12.
So we still have 12 left. Where do those 12 go? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Do we put some around hydrogen? No. It only is looking to get a duet, right? 2 electrons. It already has those 2 in that bond. That's it. That's our Lewis structure. So then what is our steric number around the carbon? Go ahead and click in your answer if you have not already. I think most people have. Let's go ahead and close out. 2/3, 3/4 of class said that the steric number is 4. I agree. Steric number is not based on the number of electrons. It's based on the number of groups of electron. So a bond is one group, or a domain. Let's ask another question that's maybe a little more complicated. It's not on your paper. What is the steric number around a chlorine, one of the chlorines in this molecule? Maybe to simplify, we'll identify one chlorine, so we're all talking about the same thing, but they are identical. So what's the steric number around that chlorine? Click in your answer then ask your neighbor if they have a similar thought. All right, a couple more seconds. Make sure you have your response clicked in. Chapter 4. All right. We have two answers that are the majority answers. We have a steric number of 1, and we have a steric number of 4. Would anyone like to defend one of those two answers? Justin?
I put the steric number as 4 because the steric number equals the number of electron groups. And on the chlorine atom, there's 3 lone pairs and there's 1 single pair.
Does anyone want to argue that succinct explanation? That was pretty nice. Thanks, Dustin. So I agree. So the steric number around those chlorine atoms is 4 because each lone pair is a group or a domain of electrons. All right. Let's... Oh, I did have that on there. So let's then talk about...
Wait, could you explain steric number one more time?
Can I get another voice? Do you want me to do it one time or someone else? Let's have Kai do it.
The steric number is the number of electron groups around an element.
Fantastic. So to build on that, do you want to do one more example? Let's do, so up on the screen I have CO2 shown, the molecule of CO2. What's the steric number around the oxygen? I'll circle 1 just so we're talking about the same one. The oxygen that's circled. Go ahead and click in your response. What's the steric number around that oxygen? Let's do this pretty quick. The one that's circled, right. All right, we're closing out. So we have 3 responses. We have a steric number of 1, a steric number of 3, and a steric number of 4. Does anyone want to defend one of those answers? Cassandra?
I say 3 because there are 3 different electron clouds, but the double bond counts as 1.
Using some really awesome terminology, clouds. I love it. So the double bond is one domain or group or cloud of electrons. Each of the lone pairs is 1 as well. So that's a steric number of 3 around each of those oxygens. The carbon then, what's the steric number around carbon? 2, because there's just 2 domains of electrons around that. All right, so from that, we're going to be even more specific. So we're just saying domains of electrons. So instead of just saying domains, I'm going to be more specific, and we're going to use a special notation called the AXE notation. And I think you guys did this some in lab.
We don't actually go into the terminology, but they do at least do out the numbers for them.
Okay. So I'm just going to give you 2 examples here for carbon. A says, okay, in this molecule, here's the atom we're looking at. A is any atom. It's not, there's obviously no atom of A. So there's A, and for around carbon, we say it's X2. Around the oxygen, we say it's A is the oxygen, X, E2. I want you to talk to your neighbor and try to figure out what the X's represent, what the E's represent, and how those are related to the steric number that we just talked about. Try to keep a little distance from the students with my illness. So let's see if you got it. Go ahead and type in what the AXE representation would be for carbon in the molecule that we just did, CH2, Cl2, dichloromethane. Try to figure out your neighbor. Type in probably can't do small subscript, so just do numbers beside letters. Go ahead and try to enter something, and then we'll discuss from that point. Just wait for this to be right. It's always about around one atom. All right, a couple more seconds. Go ahead and submit a response. Can be a starting point for discussion. All right, I'm going to close it out. So what I wanted to see typed in was something that had an A, and then either something that had an X or something that had an E, and how many of each of those. So my responses look very different from that. They just had a number. So do you want to try one more time? So these are two examples. So the carbon in CO2 is AX2. Is there an E? Okay. What does E mean then? Oxygen is AXE2. That's this oxygen here. So what do the X's mean? What do the E's mean? And how many does carbon in CH2Cl2 have? You have the Lewis structure in front of you. You can't subscript it. Unless you figure out how, and I'm impressed. All right, a couple more seconds. So it has to have an A, then either an X or an E, or both. All right, a couple more seconds. And it looks like a bit of a mess. Would anyone like to try to take a stab at what it would be, and hence what the X's and the E's mean? Sebastian? There's only one of them.
Right. And the E's, which is the lone pairs, which the oxygen have two of them, so subscript 2.
So then how does the AXE notation, as Lavoisier very nicely described, how does that relate to the steric number? Courtney? Say a little louder. What do you mean? Jocelyn? What add up? So what's the steric number for this oxygen? 3, and we have 1 X and 2 E's, that's 3. What's the steric number for the carbon? 2, and we only have 2 total. And there's E0, if you will, that's hiding there. So basically, the steric number is the blunt way, just saying how many domains are around it. We don't care what they are, but then we do care what they are, and this is the way we describe it. And we say, well, there are 3 domains, 1 is bonding, and 2 are non-bonding around that central atom. All right? I'm going to try another example here. So the answer for that last one for the CCl4 would be AX4. That's for the carbon in that molecule. And I know you can't do subscript 4, so it would be AX4. So then what would it be for the chlorines in that same molecule? 30 seconds at most. What is AXE for the chlorine? What would it be? With carbon. We already drew it. I'm using the same molecule. All right, we're at 45 seconds. We already drew out the Lewis structure. We just look at the Lewis structure and we submit our answer. Closing out. Done. All right, we have 41% of the class that thinks it's AXE3. If you notice here at the bottom, this actually says the same thing as the first answer, the AX1E3. Which one do you think is best to use? In chemistry, we try to be as simple and as clean as possible. So if they're... Whoever said that really is kind of comical. It's true. It is. But we would just do AXE3 if we wanted for 1X. So I agree with the top answer. That there's AX, there's 1X, and there are 3 lone pairs, so that's E3. All right.
If on like the exam, or
Can you say it a bit louder so people in the back can answer?
if a question like this were on the exam, would you mark it wrong if we put AX1E3 or
Just don't do it. Just do it simpler. So the question was, on an exam, would AX1E3 be counted wrong? I don't want to have to do that to figure that out. So just simplify. So AXE3. AX, there's 1X. So you wouldn't do X1, you would just do X. AXE3. So the way that this would work on an exam is I would give you a molecule and I'd point at an atom and I'd say, what's the AXE group for that and what's the steric number for that? You'd have to be able to look at it from a Lewis structure, or you'd have to draw a Lewis structure and then determine that off of it. So let's go ahead and do exactly that. So what would the AXE be for H? How many lone pairs does that have? How many bonds? So 0 E's. How many X's? How many X's? Any hydrogen? All at 1 bond. That's all hydrogen gets.
Oh, let's go by the bond. So that's why.
All right, is everyone working this one out? Should be a great example question. Sebastian. Give her like an ID or something, just to make sure you remember to get it back. All right, we have 35 responses.
Hang on, put it in. Where's it?
As we're getting the last couple of responses in, let's talk process. What's the process for answering a question like this? Kisa, can you explain your process? Okay, can you answer this question first and then ask yours?
Oh, explain the process
Yeah.
for it? I mean, like, for me, I was just like, oh my God, there's like 30 seconds, and I gotta do this, and so many answers. So I was just like, water, H2O, and then I was like, all right, O's gotta be in the middle, O has 6, H has 1 each, put them on the sides, and count them out, so that's like 2 and 2. So AX2E2 was my answer, but it's actually, they don't go, like, the way I drew it was like this. I don't know if y'all can see that.
Perfect. I'm going to draw that up on the board because I love that.
It's not actually like that because water is polar, because you know how water sinks with gravity and stuff? And so it's actually like those lone pairs have a much, like, have a lot more force. And so they go out and, alright.
So it doesn't have anything to do about why water sinks. Well, it depends on where it goes. That's a whole other conversation. Okay. Here is a water molecule. Okay? So step 1, which was said in maybe a couple more words, draw a Lewis structure. If you don't have a Lewis structure, you can't answer this question. Once you have a Lewis structure, maybe you already know what the Lewis structure looks like because you've seen it before, but you might want to draw it out to check. And then you say, well, how many domains are there in total? How many of those are bonding and how many are non-bonding? And if we look at that molecule, how many bonding domains do we have on the oxygen? 2, 1 of each the hydrogens. How many non-bonding domains? 2. So we have AX2, E2. And I really like that Kisa drew it this way first, because everybody knows that water looks like this, right? But what if we looked at it from this angle?
Looks like a nose.
Okay, so what I'm trying to say is that in 2 dimensions, if we turn it the right way and draw it in 2 dimensions, it looks exactly like what she drew there. But it doesn't tell the whole story. What's not being shown by the drawing on the board that we know is true, even though it looks like this? Yeah, it's bent. There's 2 lone pairs. But what's the difference in my hand versus there? 3-dimensional. So these 2 bonds are exactly there, but they're pointed back into the paper. Or you could say they're pointed out of the paper, and the lone pairs are pointed the other direction. And that makes all the difference. That makes a difference of a water molecule that would be a gas at room temperature versus one that is a liquid at room temperature. Maybe that's what you were getting at. Monica?
So does the drawing, I mean, because I put mine with the oxygen in the middle and the 2 main.
So we could draw this a ton of different ways. And one of the things you're told initially is always draw 4 groups around the central atom and draw them equally spaced, right? And we're going to do that, but we are going to be thinking about some of the things you did in your lab. You built some of these molecules, and you know that they don't look like that. Why are both of these... What's wrong about if they literally were either 180 degrees from each other in a line, or if they were 90 degrees from each other? Why is that not physically possible? What did you learn in lab? Maybe talk to your neighbor. What did you learn in lab about why this is physically impossible? What's the big takeaway of why that water doesn't exist like this? So I like that I saw some people with their hands trying to show stuff. Well, what is that? Enlighten us with some of your conversations, please. Would anyone care to share? Do we have any friends in the class who'd be willing to share? No? Kalia, why don't you add your voice to the conversation? So I think that that's maybe the second level of complexity. There's an even simpler level of complexity. Who wants to say what the simplest reason is why it would never exist in a straight line? Jessica? Do you want to share?
Yes. Because of the polarity of the hydrogen atoms, they're pulling away from or they're trying to pull the oxygen in different directions, and that way that's making them.
So we're kind of jumping a little bit ahead, that once we know the shape, then we can talk about where electron density is going to be the highest and the lowest. But before we go that far, it's way simpler than that. Jocelyn? What do you mean? Oh, you're saying two water molecules. Once again, that's more thinking about once we know the shape, what the properties become because of that. So let's hold off on that. What charge are electrons? What happens if you take two things that are negatively charged and you put them close together? Boof. They push apart. So if we only had two domains of electrons, let's say I drew CO2 like this. What is super wrong about that? And why? What's going to repel each other?
The electrons, the lone pair.
Not even the lone pairs. The bonding electrons. So it's like taking two things that are highly negatively charged, right? Each of these is 4 electrons that are forced into these bonds. And you're going to say they're going to stay like this? What's going to happen if you let them go? Boof. And they're going to equalize out. So if they get past 180, they're going to push back, because now they're repelling here. If they come forward, they're going to repel here. They go this way, repel, right? If my body is that central carbon. So this theory is called VSEPR. It's the valence electrons we're talking about, right? Valence shell. That's valence shell pair electron repulsion. Would you say VSEPR? It's kind of hard to write. Valence shell pair electron repulsion. It's just a fancy term to say that electrons repel each other. So if we go back to Rakaya's really nice definition, I think it was her that said it, about a domain of electrons, and Cassandra added a cloud of electrons, right? However many electrons we have in one of these defined areas, which we define from our Lewis structure. Lewis structures are still really important, right? They're the first step. If we don't have the Lewis structure, we can't do any of this other stuff. Once we know how many domains of electrons we have, now we know that each one of those domains is going to try to spread as far as it can from all the other ones. Sometimes it can do that in 2 dimensions. CO2 can end up in a line which you can draw in 2 dimensions. What if we have 3 domains, a steric number of 3? Can those spread out in one plane?
No.
Or do they have to go in 3 dimensions to spread out? Talk to your neighbor for 30 seconds. Do they need to spread out in 2 or 3 dimensions if you have a steric number of 3? All right, so raise your hand if you think they can do it in 2D. We don't need 3 dimensions. Raise your hand if you think they need 3 dimensions to spread out. If you have 3 things and they want to get as far away from each other as possible, how do they do that? What does that shape look like?
A triangle.
They spread out in a triangle. Is it a triangle that is in a pyramid shape? Or is it in a plane?
Plane.
Trigonal, right? 3-sided. Planar.
Planer.
You know those names that you guys had in the lab? All those names are based off what it looks like. A lot of times it can be super easy to try to memorize that whole list of table. If you have this AXE or this, many things around it, it's this name and this. Don't do any of that. You're just a waste of brain space. So if you have 3 things around a central atom, what would the AXE be for this, by the way? It's just AX3. I didn't put any E's around it. Is this what it would look like? Is that as far as all of them can get away from each other? What would I change? So let's change that. That can spread out a bit more. There we go. All 3 are spread out. It is a triangle, and it's in a plane. Because if one goes down, it ends up closer to the 2 in the bottom. If it comes up, same. If it goes left or right, it's closer. So all we want to think about is, how far can everything get away from each other? What if we have one of these was an E instead? Would that change? Does that change where those domains are going to be in space? Still 3. 1, 2, 3. They can't get any further away than this. Then we add on to that what Kalia was saying. And that technically, these electrons are actually a little closer to the atom because they're not shared between 2, right? They're just on 1. So they take up a little more space, so they push these back a little bit more. Overall, they're basically the same. We basically say it's identical. So what if we have instead 4 things? Let's say we have AX4. What does that look like in space? Can we do that in 2 dimensions, or do we need 3D for that? AX4. Try to describe what that looks like. You can try to draw it if you want.
It looks like this.
This is one of my favorite websites.
Oh, when you watch videos on YouTube about this?
So we have 2 right now. Doesn't matter if they're bonding or non-bonding. We add a 3rd. You can click on this and you can add whether it's a single or double bond or a lone pair. So see how they're all in a plane right now? And why, when I move this, are the other ones moving? Can you see the repulsion? How cool is that? You can kind of line it up in a plane. Maybe not. There you go. Now they're all in a plane. But if we add a 4th one, is there any way we can put this all in one plane? No. What's that shape called? You can turn that on down here. So I'll send out the link to this website. It's called PhET Simulations for Molecular Shapes. What's the difference between these two? Did you get into that? Molecular geometry and electron geometry?
Yeah.
They're the same. Is that always true?
No.
Okay, so how do I make the electron geometry change but keep the molecular geometry the same? Add a lone pair. Nope. Molecular geometry is different. So if I have a steric number of 4, what is my molecular geometry always going to be? Let's take away another bond and put a lone pair in place. So our electron geometry is still going to be tetrahedral, even if I removed all of the bond except for one. What atom does this remind us of? We were looking at earlier. This purple thing right here would be what atom that we played with before? Did carbon have 3 lone pairs around it and 1 bond?
Chlorine.
This was the chlorine in CH2Cl2. So if you're trying to figure out where all these names come from, this simulation is fantastic for it. Because you can build a shape, you can rotate it in 3 dimensions, you can kind of get to see. Why is this shape, for a steric number of 4, always called tetrahedral? What does tetrahedron mean?
4 electron group.
Tetra is 4.
So, yes, tetra is 4. What is hedron? Hedron. Dodecahedron. Something to do with geometry, right? It's how many sides a shape has. So if we go back to an even simpler version of this, and we were to connect these 3 atoms on one side and put a face on that, what shape is that? It's a triangle between these 3, triangle between the top 3, between these 3, and these 3. How many total sides is that? 4 sides. That's where the tetrahedral comes from. It's a 4-sided shape. Is that the same? What is the difference in the molecular geometry? So let's do this instead. Can someone explain, I want you to talk in your groups first, why these 2 are now different and where this name on the left comes from? Go ahead, talk in your groups. Why are the 2 names different and where does the name on the left, the molecular geometry, come from? This trigonal pyramidal. Which way? Where do you want the lone pair? Like a little octopus squid thing. So let's try to answer that first question. Why are those 2 names different now? The electron geometry is still tetrahedral, but the molecular geometry is now a different name. Tony, would you like to share your group's discussion? Sarah, did you want to share?
I probably can explain part of it.
Okay, great.
So where the lone pairs are, because they're closer, it's automatically going to push the other ones further away from it.
Okay, so that is even the more extreme version of the explanation. So let's actually come back to what the lone pair does differently than the other steric groups. Even before we talk about that, let's just talk about what the steric number is and the difference between the electron geometry and the molecular geometry. Dustin?
Kind of a question. Well, since it has to do with geometry, if you made it into an actual shape,
What into a shape?
if you, the molecule, if you made it into a shape, like a pyramid or such, it'd still have 4 sides, making it tetrahedral, but because the lone pair kind of creates a different size, you know what I'm trying to say? Because I might not know what I'm trying to say.
So I like 2 things you talked about. So you said, honestly, any pyramid has 4 sides. And your tetrahedron has 4 sides. What the hell? So I would just say that the tetrahedron is that 4-sided shape where you're thinking about where are the corners of all 4 of these things when they're spread as far apart from each other as they can possibly go. So we still have an electron geometry that is that. So we still have the electron geometry, the edge of it's out here at the top, and then we have the 4 corners. So it's still a tetrahedron. So then why is the molecular geometry different? What sets that apart? Shelby? So if we're talking about the x's and the e's versus the steric number, which one uses the steric number, which one uses the x's or the e's or both? So the molecular geometry only considers the x's where they are in space. What about the electron geometry? The steric number or both. So the electron geometry is where are all the domains, and then based off of the electron geometry, we say, okay, well, then off of that, where did these ones end up, the x's end up? Do we see that? So, can we ignore the E when we talk about the molecular geometry? If we ignore it, then it's just AX3. Is that trigonal pyramidal? No. If we only have AX3, it's trigonal planar, right? They're all in the same plane. So one thing that a lot of people get confused when they start doing this, and they start picturing a molecule in 3D, is they say, well, this one you just ignore the lone pairs. You can't ignore the lone pairs, but you're saying, where did the X groups, where do the bonding domains end up in space? Because of how many total domains there are. So if we look at this shape here, how does this trigonal pyramidal describe where those atoms are and the bonding domains are in space? What does trigonal mean?
3.
The triangle, right? 3. And then pyramidal? It's a pyramid. Can you see how there's a 3-sided base with all the white atoms, and then there's a pyramid that comes to the top of the purple one? Dylan?
Is there a relation between like the hedral and cathedral?
Probably. There's a lot of shapes in a church.
By the way, it's
I don't know I'd go that far. I don't know enough about it.
hedral.
So then, if we change this to AX2E2, I want you to write down what is the molecular shape and what is the, let me write this down. So I want to say if we do AX2E2, what is the electron geometry and what is the molecular shape? Think about which one of those might be the same from what we have here, which one of them might change. Should we do this as a clicker question? As long as you can visualize it, because sometimes it's hard the way those are drawn, but that one actually looks decent. All right, let's get a volunteer. Can I get one of you two ladies to share either one? Pick electron geometry or molecular shape.
I chose for electron geometry tetrahedral and linear for the molecular.
So let's start with the electron geometry tetrahedral. Why did you say that?
Because there are four, the steric number is 4, so we know there's 4 bonds.
There's 4 domains. Because not all of them are bonding, right? Only 2 of them are bonding.
Right.
2 of them are non-bonding. And then you said molecular shape is linear.
I'm not sure about that.
Okay, so let's take a look. Let's actually make it. Let's see what happens. I think I got to get rid of. And the cool thing is that if you're testing yourself for exam 2, you can go through and you can predict what they are, make them, and look at that, kind of go through your process. So I'm going to remove one of the bonds. I'm going to add a lone pair. So looks like electron geometry is tetrahedral, like you said, because it's a steric number. If we move it like this, kind of looks linear. But what might we have forgotten if we said linear? Because it says bent. Jay? You were doing a little thing with your hand? Okay. Do you want to say that out loud?
I guess, well, I know, because you said, like, you'll be forgetting the 2 bone pairs. You'll be forgetting the 2 bone pairs if you put it linear. And so when I pictured it in my head, it looked funny, so I just thought. But it was the only one that wasn't tried on up here.
Yeah. So they're in a plane, but it's much easier, going back to what I said before, chemists like to say things as simply as we can. I know you don't believe me, but these guys are bent. Is there any other way to get a bent shape? Can we just do AX2 and get bent? So here's AX2. That's linear. So how do you get bent? Donald? So actually, it doesn't matter what bonds you have. If you have AX2E, then you also get bent. So bent doesn't tell you what the electron pair geometry is.
So that E doesn't go on the X's, it goes on the A.
You're always talking about around the central atom. This is your A. So what's attached to your A?
Okay.
All right, y'all. So for class on Wednesday, we're going to be taking the 3-dimensional shape, and then we're going to be saying, well, what properties do those bonds have? We're now saying that they're not all just anywhere in space. They have specific arrangements. How does electronegativity of those atoms influence them? So that's chapters, I think, 4.8, 4.9. We're towards the end of chapter 4. So if you haven't gotten started in chapter 4, it's a good place to get going. Hope you have a good night.